All right. Different than the synchronous machine, the field and the rotor spin at the same speed. All right. If I look at a cross section of the induction machine is much more frequently used as a motor. All the homework problems you guys have, the synchronous machine is being used as a generator. Typically, I focus on synchronous machine can be a generator and a motor. Induction machine can be a generator and a motor. There's no reason why they can't do both. But more commonly, the induction machine is used as a motor. More commonly, synchronous machine we think of as a generator. Okay. All right. So in terms of the way this thing is set up, you've got windings on the rotor and windings on the stator. What did I say? I've got basically a three-phase set of windings on the stator and a three-phase set of windings on the rotor. R is rotor, S is stator. Okay. This is my typical phasors that I would have for the voltage. And then I have these phasors for the current on the stator. What's different? Well, the current could be phase shifted. There could be a power factor. Okay. All right. Now, the rotor windings. I showed you what the rotor windings look like. What do they typically look like? It's not windings per se. It's what? What did I call it? Squirrel cage, not bird cage. Squirrel cage, right? Basically, you get, it looks like you'd have a rodent living inside that thing, basically running around, right? So basically, the rotor windings then effectively are short circuited. So we're not applying any voltages to them. How did this thing work? Well, at zero speed, so it's starting before the motor starts. You have the rotor sitting there stationary. You put currents into the stator windings, and you had a magnetic field that started rotating around the air gap. That magnetic field rotating around the air gap did what inside the rotor windings? What happened inside the rotor winding? Yeah, induces a voltage, right? And if the field moves at 60 hertz, it's going to induce a 60 hertz current in the rotor, and the rotor is going to start to accelerate because there's going to be a force on that current. And it's going to spin up until it gets to what we call synchronous speed, which is where essentially the rotor, the stator field is moving at the same speed as the rotor. If the stator field and the rotor move at the same speed, effectively we said there is no current induced, right? I called that synchronous speed. If there's no current in the rotor, there can also be no torque. So that we call the no load condition, right? So up to synchronous speed basically was the no load condition. So I walked through the basics of how I would have a model for this thing, right? And this is my basic model for what this thing looks like. All right. For a single phase, basically line to neutral, I have a resistor. So we said, first of all, if I'm inducing a current in the rotor, I can think of this thing as kind of like what other device that we've seen before? What's that? A transformer, right? I'm basically inducing a current in a secondary side. So this was me moving essentially the stuff on the secondary over. This X1 and X2, those are leakage inductances, all right? Which in a transformer, we had the magnetizing inductance, and then we had the two leakage inductances. So that's basically what this is. The thing that's different about this is I have this guy over here, R2 over S. So what was S? We defined that the other day. What did I define S to be? What was the word I even used for it? Slip, right? So basically what we say is slip is the difference between, if I go back here for a second, right? Slip, we define a couple of important frequencies, right? So if I'm talking about the electrical frequency in the stator, that's the frequency of the currents and voltages that are applied on the stator. There's the rotor mechanical frequency, omega m, all right? Then there's the frequency of the currents that are induced in the rotor. That's the difference between the speeds of the two fields, okay? And then what I do is I define basically what is the slip, all right? The slip essentially is a percent difference away from the maximum possible speeds, okay? And I wrote that two different ways, all right? And I'll use it typically this way here, right? Where I say slip is equal to omega s minus omega m divided by omega s. Omega S is what I call the synchronous speed. It's the maximum speed this thing can ever reach. And it's always equal to, so when the rotor and the field, when the rotor and the stator are synchronized to each other, there's no torque being produced. It's basically the 60 hertz line frequency divided by the number of poles within, or the number of pole pairs inside this thing. So divided by P over 2. All right. So what that says, just to deal with that for a second, if I had, just as an example, a 2-pole machine, I always have, do it this way. Let's see. Let me do it. So omega slash F and synchronous speed slash, I don't like talking in terms of radians per second, so I'm going to do it in terms of hertz, right? And then there would be, let's see, the mechanicals. Yeah, let's just do it that way. Let's just focus on those two values, right? If I have 60 hertz, and I had a 2-pole machine, what would be the synchronous speed? What would be the maximum possible speed if I had a 2-pole machine? 60, okay? If I had a 4-pole, so the electrical frequency is still 60. What's the maximum speed I can go then? 30, right? So the mechanical speed, if I look at that, so the mechanical speed is always less than or equal to 60. Here it's less than or equal to 30. All right, that's kind of the important thing. And if I do those in RPM, right, that's going to be 3,600 RPM. What would this be? What's 30 in RPM? 1,800. All right. And so similarly here, right? What if I had a 6-pole machine? What would that be? Yeah, so you take 60 and divide by 3, so it would be 20 hertz. What's that work out to be? I think that's 1,200 RPM. I think. Yeah. Right. So, and you can go through, you look at different motors, you'll always see that the rated speed is always a little bit less than the synchronous speed, right? I showed you an example nameplate where the motor was a 10 horsepower motor, right? Where it had a rated speed of about 1,750 RPM. So that's a 4-pole motor, right? And so, you'll typically see it fairly close, all right? The slip is the percent difference. So if I look at slip, all right, it's omega S minus omega M divided by omega S. Obviously, I can do that in terms of hertz, or I can do that in terms of RPM as well, right? So let's just say that I have a 4-pole machine as an example. And so its synchronous speed, let's say, is 30 hertz, right? What's the slip if I'm at synchronous speed? This thing's moving at synchronous speed. What would the slip be at synchronous speed? What's that? 0, all right? At synchronous. All right, so we say that basically it's at that, when we're saying it's 0 slip away from its maximum. If I looked at this as worst case scenario would be slip equal to 1 or 100% away from its maximum speed. What speed would that occur at? What mechanical speed would that be? Yeah, if it's not moving at 0, right? So essentially what we see is the slip's going to go through that range, right? And so the slip basically is what, in all of these circuit models, look at what you guys are dealing with in the DC circuit, DC machine that you're dealing with now. The DC machine has that voltage source, K times omega M, right? The synchronous machine that you're dealing with now has that voltage source that has omega M IF, right? That's it's a phasor in that case. That guy is relating to the voltage being induced by the field coil, right? Same thing is true in the DC machine. In this guy, what those voltage sources represent basically is the energy conversion between the electrical and mechanical domain. That, in this case, the induction machine, that's represented through this R over S resistor, right? So this R2 over S resistor represents the energy conversion piece. So I went through last time and I basically summarized all of the key results for the machine. I basically, here is a summary. I walked through, that's the circuit model. Basically what I said is, we talked about the power across the air gap, right? So basically this is the secondary side of the machine. That's the secondary of the transformers. That's on the rotor side. All right. So we said that the power across the air gap is how much power gets into that R2 over S resistor. Some of that power is loss in the resistance. Just the fact that there's current flow in there means there's an I squared R. We derived out the mechanical power, which is the power that actually, so when I say the mechanical power, what I mean is the power that actually that flows into the machine electrically and basically becomes torque times speed at the shaft. Okay. And then what we did was I divided this by, how did I get from here to here? I'll ask you guys, how did I get from here to here? How do I get from power, torque? Divided by the mechanical speed, right? And I manipulate that so it's in terms of the synchronous speed. All right. All right. So those are our key relationships. And the important thing is, how do I analyze this circuit? So if I give you a problem and I said, all right, and we're gonna look at these problems a couple of different ways. First of all, if you go and buy an induction motor, right, and you can do that, you can buy an induction motor anyway. Go to Grainger. That's my favorite place to get them. I guess I'll go to Grainger or whatever online, McMaster-Carr. Try to buy an induction motor. If you buy one, you don't get a data sheet that says R1 is 3 ohms and X2 is 2 ohms. That doesn't come like that. What they tell you at best is they give you something like these curves right here, which shows the current versus percent of synchronous speed. All right. And torque versus percent of synchronous speed. Now, it may also show you some other stuff. Like, for instance, it may show you the power versus speed. It may show you the power factor versus speed. It may show you the efficiency versus speed. All right. But they're never going to tell you more than, they're not going to tell you the parameters. The only time they tell you the parameters, and when I say the parameters, I mean like the R's, the L's, the C's. They only tell you that if you pay them money to do that. All right. And usually you're only doing that if you're getting like 1,000 horsepower type of motors. All right. Not your run of the mill stuff. All right. So what I'm showing here, let's just see. So it's showing PU torque. All right. It means per unit torque. All right. So that's basically as a function of the rated torque on the machine. All right. So what it says here is percent of synchronous speed. So what does that mean? So percent at 100% synchronous speed, that means that this is omega S right here, and this is 0 right here. So in terms of slip, this is a slip equal to 0, and this is a slip equal to 1. All right. So at 0 slip, I'm at 100% speed. What's my torque at 100% speed? This is my torque curve here. All right. That's my torque curve. What's my torque at 100% speed? 0. Now, why does that make sense in terms of this circuit? Right. At 100% speed, my slip is 0. So how much current is flowing over here in this side of the circuit? None, because the resistance is infinite. I got an open circuit over there, right? Basically what it represents. The trick about this is if I tell you to analyze this circuit, you can't just analyze it straight away. Even if I gave you all the R's and X's and everything, you wouldn't be able to do it. What would you need to know? To analyze this thing, you need to know what the mechanical operating condition is. You need to know how much torque it's delivering so that you can know, and this is the important thing, I need to know how much torque it's delivering so I can figure out what slip it's at. Okay? So what's true in general, once I reach steady state, right? The important thing in these things is I always have to follow Newton's laws, right? So I say J d omega m by dt equals torque electrical minus torque mechanical. What's true if I get to steady state? The difference between those is 0, which means what? They're equal. And what's that mean about the speed of the machine? if the net torque is 0, speed is constant. This thing's not accelerating or decelerating. It's found a happy operating point. So where does that happen? Well, that happens wherever the mechanical torque and the electrical torque are equal. This thing that says motor torque, that's the torque electrical, right? The mechanical torque, I showed here a couple of common loads, right? And in your homework, your last homework, you're going to deal with this. There's 2 common types we talk about: a constant torque load or a variable torque load. And I showed 2 examples, right? Constant torque, this would be what I call a positive displacement type of loads. This is more of a mechanical engineering problem, but basically a compressor or a piston fired pump or something like that has a constant torque. If I'm dealing with probably the majority of things that you deal with, which are pumps and fans, they are what we call centrifugal devices. And they typically have a torque that depends on speed. All right. And so what you do is you say, okay, well, where is the point at which the load torque and the motor torque equal each other? So if I'm looking at this variable torque load, that would be like right here where they intersect, right? So if I want to figure out where the machine's operating, I would say, all right, wherever those 2 curves intersect, go down and look at the slip, and that's the slip value. So what this tells me here is that he's operating, probably, I don't know, this is about 98. If it was this variable torque load, this guy would be operating about 98% of full speed, right? Which would be about 2% slip. All right. So S, if I said I was at 98% of synchronous speed, what would the S value be? 0.02. Okay. And that's pretty normal for where I would be operating. Okay. All right. So let's look at an example. I got a 500 horsepower motor. All right. Which I'm applying 2300 volts line to line. And to do this, I always have to tell you an operating speed. Right. So what I'm saying here is, let's say the machine is operating at 1773 RPM. So I've got the parameters there. And again, like I said, typically you don't know the parameters. All right. Sometimes people will try to estimate them if they need to, but that's only in the case of a large motor. 500 horsepower is getting to be what I would consider to be a big motor. Okay. It would be very, very heavy. Maybe the 500 horsepower motor is made of iron. It's pretty large and pretty heavy. Okay. All right. So where do I start with this? I want to ask a couple of questions. What's the synchronous speed in RPM? If this guy's at 7, this is a common question that I'd see on like the FE exam, right? 1773 RPM. What's the synchronous speed here? So what would synchronous be?
Speed divided by the volts in the field.
Synchronous is the maximum speed it can get to, which, if you go back, it's related to the 60 hertz frequency divided by the number of pole pairs, P divided by 2. What would be the maximum speed? First of all, if this guy's going 1773 RPM, how many poles do you think it is? 4, right? So it's 4 pole. All right. And what would be the maximum speed it could do then? 1800. That's its synchronous speed. So if I wanted to calculate the slip here, slip is basically synchronous minus the actual mechanical speed divided by synchronous. Now, I'm writing that in terms as it would be in radians per second, but obviously you could do it in RPMs, right? You should be able to see that. All right, so that would be the slip, oops, not omega, slip would be 1800 minus 1773 divided by 1800. I didn't actually calculate that. What is it? What does that work out to be? So 1800 minus 1773 divided by 1800. 0.015. Yeah, 1.5%. Right. So 0.015. Right. So 1.5% slip. So we're talking small. This should be the point at which this machine is providing 500 horsepower of mechanical output. So it's just 0.015, right? Multiply it by 100 to get percent, right? All right, so then what do I do with this information once I have it? Well, I go to the circuit model, right? So I say 2300 volts line to line. The circuit model that I created was not a line to line, but a line to neutral. We always create line to neutral circuit models. So if that's the case, if I got a line to neutral circuit, it looks like that picture right there, right? So if 2300 volts is my line to line voltage, what is VAS? What would that be? Divided by root 3, right? 2300 volts divided by the square root of 3. Okay. All right. So here's my circuit now. I want to figure out, in this particular case, my slip is 0.015. I want to figure out how much torque this thing is providing. So how would I do that? Well, let's go back and look at this. So to provide torque, what did I need to have? I needed to have current over in this branch right here. Okay. So ultimately, the torque depends on the current in that branch. If I go back to the formulas here that we worked out, basically the torque produced by the machine is related to this R2 over S and whatever I2 is. All right. So let's do that. Let's try to get to the torque. If I want to get to the torque, what should I try to figure out? I2, right? I2. So I'm going to put a voltage source here. All right. How would I solve for I2? And let me get rid of that. I derive it with standard definitions, but let's just assume it's going that direction because we know it's flowing that way. All right. How would I figure out I2?
Define the total resistance, define the total current, and do current division.
Find the total impedance and do current division. I like you. You're my kind of guy. I know. I was hoping you weren't going to tell me do mesh or nodal. That's good. I like current division better. All right. So what's the total impedance? Not R1 plus X1. Close. Not R1 plus X1. Plus JX1. There you go. R1 plus JX1. Plus JXM in parallel with X2 times JX2 plus R2 over S. Like that. All right. Now I got to use that over S in this particular. So I got to plug in that value of S equal to 0.015. All right. So if I simplify that, it becomes R1 plus JX1 plus JXM times JX2 plus R2 over S. Over what? You guys remember? The sum of those two. J, and I'll write it this way. JXM plus JX2 plus R2 over S. All right. That's my impedance. So how do I figure out what the current flowing in? So IAS, the current flowing in here, what's that? Probably. Okay, so it'd be VAS divided by Z, right? Where I could plug in that value of Z, right? Just pretty straightforward circuits. Now, if I want to figure out what's I2, how do I figure out that? Mr. Current Divider.
IAS times JXM over
Yep.
JXM plus JXM.
Yeah. That's my current divider relationship. Yeah. Yep. All right. There you go. So that'll get me to I2 fairly easily. All right. Now that's going to be a phasor, right? It's going to be a particular value in current. Now, what do I do to figure out the torque? Well, if I look back at the formula here, I basically say it's related to not directly to the phasor of the torque, but the magnitude of the phasor. That should make sense, right? Because torque is a real thing, right? It's not going to be a complex number, right? So essentially what I see here is I use this value here. So it says depends on the synchronous speed. All right. And then it depends on R2, the slip, and I2. So basically, I go in here and I just basically would calculate this guy by saying it's the torque is equal to 3 over whatever the synchronous speed is times, I don't even remember, P over 2 times the magnitude of I2 squared times R2 over S. So I do it like that. Now, what I want to do is I want to say, well, what would that end up being? Well, so if I went and calculated that, I didn't actually run through and calculate that number, but you can, right? This guy should work out to be fairly close to, essentially, that torque should be close to, because this is rated conditions, it should basically be close to 500 horsepower, whatever that is, divided by 1773 RPM, okay? It should be close to whatever that value in Newton meters. Now, what I often do is I say, all right, let's just step back for a second. And let me say, I'm looking at this right here. All right, we derived a bunch of math there. I want to think intuitively. What's going to happen to this machine at different conditions? All right, intuitively. So startup, what's the speed at startup? 0. Easy question. Omega m is equal to 0. Slip is omega s minus omega m divided by omega s. What's slip at startup? 1. Okay, 1. So if I look at that, and I look at the parameters that I have here, in this case, this circuit simplifies to, got a voltage source, I got R1, X1, XM, and then I got X2, R2. Now, if I told you, and see, this is a good question to remind ourselves, back in the case of transformers, you probably don't remember this that well, but if I have these values of leakage and these sort of what I call, those resistances are parasitic. They're the resistance of the windings, okay? So resistance of the windings should be small, ideally, or else it's probably a very inefficient machine, making a lot of heat. Leakage should be small, right? Why should leakage be small? So let's think back to transformers if you can. It's probably a worthwhile thing to remember for the bundle. Thinking about the impedance of these leakages versus the magnetizing. Which one should be bigger? Yeah, magnetizing is bigger. You don't want a lot of leakage, right? If you have a lot of leakage, that says ultimately that a lot of your magnetic fields are fringing out of the machine and they're not going across the air gap and being useful. So this value should be big relative to these. So we look at the parameters. Let's take a look here real quick. All right, so what do we see? We see that XM is about 54 ohm. All right. Everything else is on the order of 1 ohm or less. All right. So what do you think is going to happen if I have basically just looking at this circuit here? Yep, most of the current is going to flow this way. And it looks like I have essentially 2,300 volts divided by square root of 3, divided by, I mean, just magnitude wise, we've got something that's, these two are less than 1 ohm, these two are about 1 ohm. So I'm dividing this by something, you know, I'm rounding here, but let's say it's about 4 ohms. All right. Would you call that a lot? Right, that current, right? The current that we're talking about here, 2,300 divided by square root of 3. I'm not sure what that is, but that's a number that's in the thousands, right? 1,000 divided by 4, that's a big number, isn't it? Yeah, that's going to be a large number. What about if I go to synchronous speed? All right, so let's say I'm at synchronous speed. So at synchronous speed, what's true about S? S is 0, okay? So in that case, what do I have? I have R1, R1. I have X1. What do I do when S is equal to 0? I have an open circuit over there on the secondary side. So now I just have my XM. All right, and I got my voltage source VAS here. All right, and then IAS flows into it. So IAS is equal to VAS divided by all that stuff. Now magnitude wise, so this guy was, we said again, 2300 divided by square root of 3, right? And magnitude wise, at least, we're looking at essentially about 2 ohms between these two. And what was this guy, about 50 something? Yeah, 54. Right? This is going to be significantly less current than what I had before. All right. So what happens if I'm in between, if I'm at full load? Well, at full load, the slip we said was what? We calculated it to be 1.5%. So it's probably going to be a little bit more than this. So what I actually did here was I plotted two things. I'll just do it in MATLAB here. Okay. So I generated a graph for myself, which shows, let's see, that's the efficiency. Which graph? All right, here we go. I showed 2 different things here. All right. I plotted 2 different currents and I plotted it versus speed. All right, so again, my x-axis here is labeled as in RPM. So my synchronous speed for this guy was 1800. I got a blue curve and a red curve. All right. Both of them are currents. One of them is the current I2. One of them is the current what? IAS. Which one is which? Which one's the current in the rotor and which one's the current in the stator?
Most likely the bigger one,
Why is that?
because the other one is like a subset of it.
Right. So in other words, it's a current divider, right? So the current flowing in is being divided down. So the current in the rotor should be the smaller one, right? Yeah, so that's the blue. The blue is definitely I2. The red is IAS, the current flowing into the machine. I want to point out something though here. One other thing I can tell about why this is I2 is what do I see about its value here at synchronous speed? It's 0, right? Because there's no current in the rotor because at synchronous speed, the rotor is an open circuit, okay? However, there is some current flowing into the machine, right? Because there's some current going into the magnetizing inductance here, right? All right, so the other thing I noticed, where did I say this machine was operating? Well, it was 1773 RPM. So let's go here. Yeah, let's get my pointer. So it's 1773 RPM. It's somewhere around here. Close enough. All right. You can tell how steep the curve is here. All right. At 1773 RPM, this guy looks like he's around about 66 amps. That would be his, what I would call his full load amps. If you were to look on the side of the motor where it says his rated amps or his full load amps, that would be the value for this particular one. Sorry, and be careful about that. That's not the full load amps. Why is that not the full load amps? What curve am I looking at here? What curve is this? That's the rotor side. When they give you the nameplate, they're telling you the current that's flowing into the machine. So at the same speed, I would look here and say, all right, at 1773 RPM, I see that the actual current flowing into the machine is pretty close here. It's hard to get this exact. Let's call it that. Looks like it's about 116 amps. All right, that's the full load current going into the machine. All right, now what do I see about this here as I go down towards 0 speed?
Levels out.
It levels out, but it levels out at what? Levels, yeah, levels at a very high current. In fact, so I see that at the rated condition, this guy's about 116 or so. Looks like by the time he's up there, he's almost a factor of 6 higher, right? He's getting close to 600 amps there, right? So that kind of tells me an important thing. That totally jives with what we just said, first of all, right? What we said was, right, just to be clear, we said that at startup, right? At startup, most of the current's going to flow through this outer loop that I'm showing right here in this circuit, right? And so we basically said it's going to be a big number divided by a small number, right? That big number divided by small number is going to be a big number, right? When I look at close to rated conditions, I'm looking at big number divided by a much bigger number. So that's going to be a smaller number, right? So intuitively, what you're seeing in that picture there, right? What we're seeing in this picture makes some sense. This is synchronous speed or the full load condition. Specifically what I'm showing, this is full load, this is synchronous speed. Here, all the way to the left is startup, right? That current's gone up significantly. What I sometimes call that, that point all the way over there at low speed or at zero speed, that basically sometimes called LRA or locked rotor amps. All right, sometimes called the stall current. Basically, this is the current. Why would I call it the stall current? Yeah, when it's stalled. In fact, what will happen is if for some reason, let's say, for example, let me get to the torque curve, right? Let me get to the torque curve. I'll talk about what I'm going to say. But the machine can stall during startup, all right? And it can get stuck there. It's really bad if the machine gets stuck at zero speed. If the machine stalls and gets stuck at zero speed, it's producing a lot of torque, trying to get itself going, but it's not able to move. What's going to happen to the temperature of that motor? It's going to increase significantly, right? The current here, I mean, this is what's important. That current, let's call it a factor of 5, all right? Higher than it is at rated, okay? Factor of 5 means how much more heating is happening in there? 25 times more heating, right? Because effectively it's 5 squared. Remember, it's I squared R. So there's 25 times more heating. That guy's getting hot fast. And that will definitely have an impact, a pretty negative impact on the windings in that machine. All right. So that's our basic, concept. Now, if I go in and look at the torque, so what I would do is I would take the magnitude of I2, the blue curve, squared times R2 over S. Right, and I would see what the torque looks like. All right, so here I've shown the torque and I've shown the input power and the mechanical power. So what do I mean when I say the mechanical? What do you mean by the mechanical power versus the input power? What do you think the input power is, first of all? Hopefully input makes sense. What do you think the input power is? The input, right? The input to the machine. Basically, it's the power going into from the VAS source. It's basically the power going in from the source into the machine, right? The mechanical power is where? It's the power actually being transferred to work at the shaft. So it's the torque times speed at the shaft. Okay. Which one? So I'll tell you, one of these two curves is the mechanical power and one's the input power. Which one would be the mechanical power? Smaller. Now, one reason I can see that fairly easily is if I look at this curve here, it's equal to 0 basically, right? At full speed, right? Because at full speed, the machine's making no torque, right? There's no current being induced over there. It's also 0 here. Now, let's think about that for a second. This guy is the torque. Oh, I can't write on that. Oops, what did I do? Uh-oh. Yep, it is. Yeah, so it is. Yeah, so yeah, let me touch on that point here in a second. But basically, this upper curve here is the torque of the machine. All right. So you see that guy starts out low, goes up high, and then basically comes back down to a lower value. And we typically are operating over here. So if I look at where this guy would be operating, we said his operating point was 1773 RPM. So that's somewhere around here. All right. So it tells me he's making about 1,300 Newton meters of torque. So let's look at the yellow curve, the mechanical power. How many horsepower did I say this machine was? 500. All right, so let's go to about 1773. All right, so we see at that point, he's kind of around about 400 or so horsepower. All right, so he could go a little bit higher than he is at this particular point at where he's operating. All right, but the important thing here is if we look at this, all right, so let's look at the mechanical power is 0 at 0 speed and 0 at full speed. Why is it 0 at full speed? There was no current in the rotor at full speed, which means there was no torque. So look at the torque curve. The torque is 0 at full speed, right? Why at 0 speed is there also no power? There's definitely some torque. There has to be torque. Why is the mechanical power 0 at 0 speed? Well, what's torque equal to, or what's power equal to mechanically? Torque times speed. So what's my speed at 0 speed? 0, right? So it makes sense that it's 0 at both ends. All right. Now, here's the thing we think about. So back to the question about the currents being high and the stall condition here. So let me go to, I posted this here on my slide. All right. So there's the torque and the powers, right? So if, let's say I was operating this thing against a constant load torque, right? So I said, let's say 1,000, actually let's do 500 Newton meters. Let's say I operated this guy on a constant 500 Newton meter torque. So my torque mechanical is just 500 Newton meters. Where this guy would operate, you would look to see where does the 500 Newton meter line intersect with that blue curve. What's the slip at that point? And you plug that in to do all your analysis. All right, now let's say instead that I decided to operate this at 2,000 Newton meters. Okay. What would happen if I operated this thing against a 2,000 Newton meter load? What's that? Yeah, there's 2 points where it intersects, right? Here and there, right? Let's think about what's going to happen in trying to start this motor. So interestingly here, so what's supposed to happen? So Newton's law, J d omega m by dt, right, is what? Newton's law, how do we write that? You're used to thinking now of the homework that you currently are working on, which has generator. So it's mechanical accelerates, electrical slows down. If I have a motor, what is it? The opposite of that. Electrical speeds up, mechanical slows down. This is if I have a motor. If I have a motor, electrical accelerates, mechanical slows, right? It has to turn something. And a generator is the opposite. I have mechanical torque going in, electrical torque basically representing the opposition coming from the currents flowing out. So in this case, if I look at this, this is what I'm supposed to have, right? Do I have that in this picture right here? If my mechanical torque was 2,000 Newton meters? So at 0 speed, let's say I started out at 0 speed and I accelerated the motor. At 0 speed, what do I have in this picture? This is my mechanical, this is my electrical. Which one's bigger? The mechanical. If mechanical is bigger than electrical, what is that? I said, that's not a motor, that's a generator. All right. So But the reality is, I mean, so this mechanical torque though is basically, if I think about it, this would be like me trying to grab the shaft really hard. Like I'm not trying to spin it, I'm just grabbing it really hard and fighting back against it. So what's the machine gonna do if there's more torque than it can make? It says it's gonna go backwards, right? It says it's gonna decelerate, but it's already sitting at 0 speed. So what's it gonna do? It's gonna get stuck there, and omega m is gonna be equal to 0. Right? These guys are going to be imbalanced, but the important thing is physically, right? This guy is going to try to make as much torque as he can. Essentially, he's going to be stuck in a stall condition. And what's true about his current? His current is going to be incredibly large, and he's stuck there. So it's going to be incredibly large until what happens? Until it blows up or the protection kicks in, right? So I'd have to have some sort of protection here. So you have a circuit breaker that might pick that up, right? If I had a really large motor, there might be a relay measuring it that would actually trip the circuit breaker or something like that. But I often care about those conditions because if I got a motor that's really big, I would worry about, what happens during those conditions, okay? All right, so that's, basics of how the induction motor works. It's fairly easy to analyze those circuits. But one thing that's kind of important, and it's one thing I want to kind of end up on, is I'm also showing you pretty old school problems. Because if I look at the way this motor works, I made this motor that essentially at full speed, no load, it's at 1800 RPM. At full load, it's at 1773 RPM. That's a pretty limited range in which it wants to operate, right? There's basically another 1773 RPMs that are kind of off the table for me. But I might want to actually do what? I might want to vary the speed of the motor. Like let's say I wanted to go at 500 RPM. That would be an absolutely terrible idea with this machine. It'd be a lot of current. What could I do instead if I wanted this machine to be used to go at a lower speed? How could I make the machine go at a lower speed more safely, perhaps? Well, I'd lower the voltage. And not more importantly, but along with it, I would lower the voltage and I would also change what about the voltage? So what sets this synchronous speed? The number of poles and what else? The frequency of the voltage. So if I set the frequency of the voltage to a lower value, I can move the synchronous speed down to a lower value, right? And I can make it operate at a different point. If I had something like a pump, that's a really good way to save energy, right? And so nowadays, you used to be you'd buy a motor and you do what's called an offline start, right? And when you do an offline start, you basically hook it up and it starts at 0 speed, it goes out to here and operates at 1 speed. Nowadays, we use what's called variable frequency drives or VFDs, basically some power electronic box that basically controls the synchronous speed that's applied to that machine to make it go faster or slower, all right? So we're going to look at that a little bit next week, all right? But this covers the majority of what we need to understand about how an induction machine works. So I will stop there.